4.4 talks about laws of logarithms. So we have 3 laws of logarithms, assuming, of course, that m and n are in the domain of logs. And every time I write a log, the assumption is that a satisfies the definition, a is bigger than 0 and not equal to 1. And in this case, we're assuming m and n are always bigger than 0. So if I take the log of the product of 2 quantities, that would be log base a, the same base of the first, plus, so the multiplication become a plus, always I think in terms of a to the x times a to the y, or even better, a to the m times a to the n is a. If you multiply in terms of the same base, you add the powers. And if I'm dividing, well, if I take a to the m divided by a to the n, I know that that's a to the m minus m. And lastly, if I take an exponential and I raise it to a power, you end up multiplying those powers. Now, you might be asking, what does exponentials have to do with logs? Well, so when you are raising a variable to a number, you could move that up front, and that's a key law that a log possesses that nothing else has. Well, it turns out logs, and exponentials are inverses, so they go hand in hand. So every time I want to remember those to be laws, that's what I remember. When you multiply 2 exponentials with the same base, you add the powers. When you divide them, you subtract the powers. And when you raise them, raise exponential to a power, you multiply those powers. Or memorize the rules as they are, whatever works. So evaluate the expression. Alright, let's get a numerical value if possible. I notice those are 2 logs with a plus in between. I could write as a single log base 6 of 3 times 12. That is log base 6 of 36. But I am aware from the previous section that 6 is 3 squared. So I could say, and those undo each other, and I am aware that the answer would be a 2. 2 logs with a minus, well, I could combine into a single log. That would be the single log base 5 of 100 divided by 4. So this is going backwards. That would be the log base 5. 100 divided by 4 is 25. And 25 is 5 squared, so we know that's a 2 as well, because the base of the log and the base of the exponential match. Here, I have a couple of options to do this. I'm going to show you the use of this. One way of doing this is for us to say this is log base 2 of 4 times 4. That is log base 2 of 4 plus log base 2 of 4. And you could say that's the log base 2 of 2 squared. And that is the log base 2. That's 2 times 2. So I could write it as the sum of 2. Same with this. And isn't that a 1, 1, 1, 1? Isn't that a 4? Or I could say this is the log base 2 of 2 to the 4th. And those undo each other, and that's simply a 4. Right? Also, I could move that up front and say that's 4 times 1, which is identical. So that's a main use of the properties of the laws if they overlap. If I glance at this problem, I would say this is the log base 3 of 1 over that's 3 squared. By moving this up, that's log base 3 of 3 to the negative 2, and those will undo each other, and I'm left with the power because the base of the log and the base of the exponential match. And there it is. And here the same deal. I notice the log is base 4, so that's where I begin. I have a 4. I want this to be an exponential with a base of 4, and that's doable. properties of exponentials. When you raise powers, you multiply. 2 times 3 is 6. And since the base of the log and the base exponential match, they undo each other. And we are left with the power. I meant to do this with a log base 3. Couple of ways of doing this problem. One way of doing this problem, and this one I'm going to show you the difference between when it evaluates and when it doesn't. So I'm going really for this time. I kind of messed up on C. So here, I'm looking for, well, you could say that's log base 3 of 4 times 4, like we did up there. And you could say that is log base 3 of 4 plus log base 3 of 4. And you say, wait a minute, that 4 is 2 times 2. So I could say that's log base 3 of 2 plus log base 3 of 2 plus log base 3 of 2 plus log base 3 of 2. And I have one of those plus 1 plus 1 plus 1. That's 4 of those. This is the long way of doing a problem. A quicker way of doing this problem is for you to say, you know what, this is the log base 3. Isn't 16 2 to the 4th? And by the third law of logs, can't you move that up front? And look at how much work that saves me. And if I look at this problem, this is natural log. Remember, this is a log base e of e to the 1. The base of the log and the base of the exponential match. And wasn't it the first property of logs? The log of any base of 1 is always 0. What if I wanted to combine those logs into 1? Well, here we have an issue. And what is that? You notice there's always a 1 or a negative 1 in front of the logs for me to be able to trace them back. If I don't see a quantity that's not a 1 or a negative 1, I could reverse the third law and make the number a power. Meaning, I could say, well, if I reverse the third law, I'm going to make that a power. I'm going to make that a power. That'll be the log base 3. Now that there's a 1 and a negative 1, well, it's simply with a minus, you always divide 25 by 11, and there it is. If I see those two logs, well, I could write those as a single log of x squared plus 3x plus 2. A minus translates into division. If I factor the top, because you know we're supposed to simplify, that will be x plus 2 into x plus 1. And wouldn't this cancel with that? And I would be left with a log base 3 of x plus 1. There are other ways of doing this problem, but we're trying to enforce the rules of logs to do these problems. Here's another set. Same deal. Well, if I really get this down, first step is to write these logs with a coefficient of 1 or negative 1. Wait, wasn't there a 1/3 somewhere? Oh boy, I forgot about the 1/3 right there. You guys should say something. 11 to the 1/3. And what's 11 to the 1/3? Isn't that the cube root of 11? My mistake. Thought I put a radical in there. So, I could say this is, and I could do this one shot if you really want. You could do it 2 at a time. You could say that's the log base 5 of 8 times x to the 5th minus log base 5 of the 4th root of y, and 2 logs with a minus in between, log base 5 of 8x to the 5th divided by the 4th root of y. Or, the algebra works out, so this is a fine answer. The algebra works out that you could write a single log base 5 Anything with a plus will go at the top of that fraction. Anything with a minus goes in the denominator, and you could save yourself both of these steps combined. So, since that's a plus, that goes at the top, that's 8. Since that's a plus, x to the 5th. Since that's a minus, and one shot, you would know that you really got it down when you get to this level. You don't have to get this level, but that will really indicate that you understand this. So one way of doing this problem is for me to say, well, I need to get rid of those coefficients because I need them to be a 1 or a negative 1. So move that as a power. Again, log is the only function that we have in science that allows you to play with powers like that. So this step is a must. From this point on, you have two options. Either you say this is, I'm going to take those two, natural log of x cubed divided by y squared, and two logs with a minus in between. You could say that's the natural log of x cubed over y squared divided by square root of x plus 3. And instead of dividing, you could multiply by the reciprocal. And there it is. Or you could say it's a single natural log. All the pluses will be at the top, all the minuses on the bottom. That's a plus because there's a plus there. That's a minus, that goes in the denominator. That's a minus, that would be in the denominator. And you could do that anytime with logs. Expand the expressions. Well, if I have the log of two terms multiplied, that's log of the first. When you multiply exponentials, you add the powers. Done. Nothing else to do. Here, you're multiplying, that's natural log of radical x plus natural log of y. I could simplify a bit more. Isn't that natural log of x to the 1/2 plus natural log of y? Can't I move this up front? So you need to be able to move forward and backwards. Why do we do that? Because we need to solve equations that involve logs. How about this? If there's a quotient that's log base b of the top minus the bottom, I normally start with the division first. There's a product there. That is natural log, that's log base b, not natural log, I apologize. That's log base b of x cubed plus log base b of y squared minus log base b of z. And if I move those powers up front, that is 3 times the log base b of x plus twice the log base b of y minus the log base b of z. Now, I could say this is going to be the log of x squared minus the log of x plus 1 to the 1/4. Move those up front. And what's the base on this log? It's really a 10. If I don't write a base, we assume that's a 10. And if I put an e, that's natural log. Special logs that my calculator could read. We are going to use that today. Suppose I have a to the x equal b to the x. One way of doing this problem is to say, you know what, I'm going to change that to log form. The base of the exponential is a b. The log will be on the left with that base of b. The side that's not a log, the power of the exponential, becomes the side that's not a log, and a remains where it is. Now, something we didn't do yet, I want to point out. Instead of memorizing the definition, now that you know about the properties, can't you log both sides? Is that allowed? Yes. If you do it to the entire side, the whole side, I could log both sides of this equation. That's allowed. You could do that. I could choose any base. You have to tell me what the base is. If you don't write anything, it's a base 10. But if you want to get rid of base, if you want to get rid of the exponential, shouldn't you choose the same base? Isn't this just x? And that's a log base b of a, which is this. So that's one way of doing it from now on. Instead of using, in case you've forgotten the definition, you just log both sides. But what if somebody would have said, you know what, but I don't want base b. I want base 10. Can you do that? Well, remember, we want to solve for x, right? We got x. Here, wouldn't you use properties of logs and move the x up front and say that's x times the log base 10 of b? And to get x by itself, can't you divide both sides by log base 10 of b? And somebody might look at this and say, wait a minute, that's pretty good, but hey, just for the sake of arguing, couldn't you have also log both sides? But used base e? Well, of course you can. Can't you move this up front and this becomes natural log of a equal x times natural log of b? And if you're solving for x, can't you divide by natural log of b? And there's x. So what does that tell us? If I have x equal a quantity and I got x equal another and x equal another, those three are equal. So what that means, this is the only formula we have, change of base formula. If I'm taking the log of a base that I don't like, if the base, so if I want to use my calculator, most calculators only read log base 10 or e, then I would say that is the log, that's the log of the argument divided by log of the base, where I could change the base of the log to whatever I like. So we're going to use this in the next example. Evaluate the following expression, round to 6 decimal places. So if I would like to find the log base 3 of log base 3 of 5. So remember, this is asking what power do you raise 3 to get a 5? So what power do you raise 3 to get a 5? That's really what you're trying to solve. Well, let's see how that works. I like natural log because it's one letter shorter than that, but it's all the same. So this is natural log of 5 divided by natural log of 3. I could get my calculator. Now some calculators could use a different base. So you could, like this does right here. But I'm just gonna, so here you could put the base in these new calculators. I could put a base of 3 if I want, of 5, and this calculator could do it. Most scientific calculators can't, and it gives you the answer. The way you're gonna do it, you're gonna say, well, it is natural log of 5, and if you have that key, you're welcome to use it, that's fine, divided by natural log of 3. And there it is, 1.469, 1.469 464 464 974, 6 decimal places. Similarly with the next problem, again, this is, in this case I'm going to use, oh, by the way, let me just make sure you see that. If I was to use a log of 5 divided by a log of 3, that would be the same thing. So if I was to use, oh, this calculator doesn't have log base 10 because you could choose the base. Okay, that's fine. So log base 10 or log base e gives you the same thing. And here I'm going to say this is natural log of 2 divided by natural log of 6. And that would be 0.386 853. And one more just to make sure that we're seeing this. This would be a natural log of 6 divided by a natural log of 1/2. And if I take natural log of 6 divided by natural log of 0.5. That would be negative 2.548 and 3 more decimals. 963. Again, the reason I'm copying this down so this would be accessible to all students. And that's pretty much it for this section.